Good morning, everybody. So today we're going to be talking about section 5.6, and I just want to give some beginning information about what we're dealing with. So we are talking about rational functions, and as we travel through this experience, this is a loaded section. We have lots of little things in there. So the first thing we're going to talk about is domain, and then we'll talk about asymptotes. Eventually, and not probably in this video, we're going to talk about a thing called a point of removable discontinuity or a removable point of discontinuity. It depends on your book. So, first of all, a rational function looks, in simplest form, something like this, like 1 over x. And if we chose a whole series of x values to plug in, and considering we can't divide by 0, we would choose like little values like 0.1, 0.01, 0.001, and we get very large values out of there when we plug in very small values. And just try it on your calculator. Do 1 divided by 0.1, and then 1 divided by 0.01, and then 1 divided by 0.001. And because we can't divide by 0, that value is not part of the domain. But we can get incredibly close to it. And what happens is you get this graph that travels off up to positive infinity. And if you come in from the left side and you use negative 0.1 and negative 0.01 and so forth, you get a graph that travels down to negative infinity. And that is the description of a vertical asymptote. Okay. You can, at the same time, generate a horizontal asymptote. There's a slight difference between a vertical and a horizontal. A vertical you cannot cross, but a horizontal you can. You can approach a horizontal with a wavy line, or you can just cross it and come up from underneath, or you can cross it and come down and get closer and closer, okay? Now, a rational function by description is some g of x, like it could be some polynomial divided by another polynomial. And what's important here is that we make sure that the denominator does not equal 0, okay? And that's where you're going to generate either asymptotes or points of removable discontinuity. Now, we're going to talk a little bit about the idea of a horizontal asymptote at y equals 0. This function, the 1 over x, will have that horizontal asymptote. And let's see if we can kind of explain why. All right, so if your y is equal to 0, that would mean what's happening is f of x, your f of x equals 0. And so you're looking at it as f of x, which is equal to 1 over x, has to be equal to 0. And so you start asking yourself, what value of x could you plug in here to make it 0? And if you think about it, what you'll eventually come to the conclusion of is that no value of x will make 1 over x 0. But what does happen is that when you take very large values of x, such as 1 million or 2 million, you get a number that's really, really tiny, really, really close to 0. So our statement is, as x approaches infinity, it will cause 1 over x to get close to 0. And so if we're looking at it graphically, we're heading way out over here, and this graph is hugging, getting closer and closer and closer to the x-axis, which is the y equals 0 line. Okay? A similar thing will happen if you travel off to x equals negative infinity, and it will hug that x-axis coming or going towards negative infinity. Okay, so we are looking at domain. Domain leads us to asymptotes, vertical. It also leads us to points of removable discontinuity. Trying to determine where the horizontal asymptotes might lie requires long division. There is another type of asymptote called an oblique asymptote, and that would look something like when your graph does this. So here's your x-axis, here's your y-axis, and it would travel down and it heads up, and you get this dotted line, and the graph would travel down and then do something like that. And so this oblique asymptote is also found by doing long division. And we'll do some examples of that as we travel through this. Okay, so just a reminder that 1 over x cannot be 1 over 0. You're not allowed to plug in that 0 or generate a 0 in that denominator. So if your expression in the denominator is like 1 over x plus 4, and this is your f of x, well, that's telling us our way to figure out what values to avoid. So we're going to subtract 4, and we get x is not equal to negative 4. That's actually the domain. X cannot be equal to negative 4. Your book does like to use interval notation. But as we creep into that negative 4, we get very, very close to it. This function is going to travel off to either positive infinity if you're coming in from the right side, or off to negative infinity if you're coming in from the left. Okay, that's a long video right there. I'm going to stop, and then I'll make another one describing some other things. Thank you.